Good afternoon. Today we will be talking about the second section of mixed signal processing. Now, last time we discussed what is mixed signal processing and what are the advantages of analog and digital signal processing. Now we'll be discussing what do we mean by reconfigurable digital circuits and architectures. Now, reconfigurable systems are becoming very popular in signal processing, especially in mixed signal processing. So let's try to understand what is the need for reconfigurable systems. So first we should know the need for a balance between speed and flexibility. Because in one hand, we are looking for a higher and higher speed because of the bandwidth requirement, especially for communication applications. And at the same time, we are also looking for flexibility for obvious reasons. And the most important reasons for flexibility is the marketing. So let's try to understand what are the advantages of software-based solutions. Typically what we call programmable processor based on von Neumann architecture. The basic advantage is the flexibility. That is the advantage of software-based solutions. Flexibility in the sense, as we have already discussed, that given a hardware platform, just by changing the software, we can change the applications. So as a result, what happens? Product development time gets reduced. And if the product development time gets reduced, the cost of the product, the development cost of the product, it goes down substantially. That means the cost of the product will be decreased. And if the cost of the product gets minimized, then the sellability of the product goes up. So that is in fact the chemistry from the business point of view. And as we are thinking of applied research, the engineering research that is oriented by the market. That means the ability to buy the product, especially for the consumer product, that will enhance the sellability of the product. And here the research. So we know that the advantages of the hardware-based solution is the high speed, and advantages of the software-based solution is flexibility. But of course, software cannot be done without having the hardware platform. Only thing is that getting the same hardware platform, just by changing the software, we can change the application. So when a product needs to be upgraded with a changing scenario of technological development, this can easily be done by changing the algorithm, means changing the software. But one drawback for the software-based solution is the speed is relatively slower compared to hardware. But everything you cannot do by hardware. Hardware, of course, a basic platform will be there, which is a programmable processor. On that, we'll be developing the software. So here we need a trade-off between speed and flexibility. So the need is to find a balance between flexibility and speed. That means to eliminate the inflexibility associated with the ASIC and to overcome the speed limitations of the conventional von Neumann processors. Now here you have to understand ASIC offers a high speed, but it is today, because of the newer and newer applications, making ASICs for each and every application is not very much cost effective, because the ASIC development time is quite high, and a risk factor associated with ASIC is very high, because today if you develop a product, that means you have to make the chips, and unless you develop at least 50,000 to 1 million chip, it is not cost effective. So if a little bit of change is required for a product, you can't do it because it is fixed. So that's why you need some flexibility. There means some kind of incurring the features of programmability within ASIC. But at the same time, the speed of the ASIC is the highest. How to do that? That means elimination of the software approach to solve a given problem without losing the flexibility of the software. Now, why you are telling this thing? Software approach means when an algorithm will be run on a software, that means on a processor. Program means sequence of instructions, and these instructions will be executed one after one sequentially. So that is the problem. So that means you need a different type of device, different type of processor, where the execution will be done at a hardware speed. That is the need of the hour. So first, let's try to understand what are the issues involved in finding a solution using state-of-the-art VLSI devices. Because at the end of the day, we have to design a VLSI chip. So what are the basic issues involved? That first we have to understand. There are 4 parameters which are very important: low cost, high speed, low power consumption, and flexibility. So these 4 parameters have to be kept in mind before you design a VLSI device. So that means an innovation to leverage flexibility and speed. So there is a need to innovate an efficient VLSI design with the following views: a balance between flexibility and speed, the cost, scalability, and lower power consumption, as we have already said. And there is a solution. And what is the solution? The solution is the programmable hardware coupled with high performance. And this programmable hardware is FPGA, field programmable gate array. So here, this is a processor, but this is not a von Neumann processor. Here, this processor will offer parallelisms. Now here, let's try to understand the concept of a system before we go into the details of that. System consists of subsystems which are interconnected. Each subsystem does a function and they are interconnected. And their combined effort will make a system. That means subsystems, they do the specific tasks and communicate among themselves. In fact, the programmable devices have been designed in such a fashion such that they can work concurrently. Many of the smaller units, they can concurrently do the function and they can cooperate among themselves. That means they can communicate to ultimately offer the final output. So, programmable hardware coupled with high performance. To solve it, we can read it out. High performance programmable hardware offers a balance between flexibility and efficiency, because potential concurrency in the algorithm can be exploited by directly mapping the algorithm onto the hardware. As I told you, that the function of the programmable hardware will be divided into smaller functions such that each smaller function can work concurrently and communicate among themselves. I'm just giving a small analogy for your quick understanding. Let's say you have to compute ax squared plus bx plus c. Now, by typical von Neumann computer, means the computer which we are used to, how do you compute? Perhaps we don't feel it, we write the program in high-level language, but actually inside the processor, how it gets executed? First, a will be multiplied by x to get ax. Then that ax will be again multiplied by x to get x square. That x square will be stored somewhere else. Then b will be multiplied by x, that is bx. So this bx will be added with the x square, so x square plus bx. Then finally that will be added with c. So many steps are involved in that. This is called sequential steps. So if you can find out what is the execution time, then you have to find out a multiplied by x, ax that is getting stored. That time will also be required. Again gets multiplied with x. In that way, you will be able to compute the time. And this computation time depends on the complexity of the algorithm, means how many multiplications have to be done or how many additions have to be done. So depending on all these things, your total computations will be required. However, if you just look at the geometry of this algorithm, you can easily find that when ax square is computed, bx plus c can be computed separately in concurrent, and then they can be added, so at least some time can be saved. So when the algorithm is more and more complex, find out which tasks can be done concurrently, and after that they can be put together. So that means parallelism within the algorithm can be exploited. Now to do that, the device should support this, otherwise you cannot do. One example, your normal von Neumann processor don't support these things. They need to be done sequentially. Here, in fact, that means you need to have a device where many of the operations can be done concurrently. In fact, programmable hardware offers this kind of features. As compared to the hardware chips, programmable devices can be customized as far as the need of the user by programming. It means these programmable devices, they need to offer some kind of language, programming language, by which you can program. And these languages are known as hardware description language, the language by which you can program the hardware. And that is the reason today FPGAs are becoming so popular. FPGA stands for Field Programmable Gate Array. And these FPGAs are basically the logic devices. And large number of logic devices, they are placed onto a single semiconductor chip, typically called VLSI or ultra VLSI devices. And there are a lot of switches such that they can be connected. I'll be discussing in details of this, but let's try to understand what should be the basic building block for FPGA. So to summarize, FPGAs are programmable hardware devices. They're not like von Neumann processors. Here, the FPGA consists of large number of small building blocks, and these building blocks are known as CLB. CLB stands for Configurable Logic Blocks. So each CLB performs a particular logic function, and they can be programmed. Now here, if we just look at this, can you see the diagram?
Yes, sir. Yes, sir.
Okay. Yes, sir. Now, at the periphery, you can find some yellow blocks. These are IOBs. IOB stands for input-output blocks. So they communicate with the external world. So they can input data and deliver data at the output. Now, green blocks are CLBs. They are logic functional block. Now here, this is a two-dimensional block. There are 4 by 4. There are 4 rows, 4 columns. Each row there are 4 CLBs. Now, there are some buses you must have noticed which connect the CLBs. And there are some ping blocks. Ping blocks are the switches. By programming the switches, means by changing the configuration of the switches, different connectivity can be established. So depending on the need of the particular problem, you can configure the switches such that a specific function can be realized. That's the whole idea. So that means when you are programming for a particular function, means what? Let's say you want to design a complex digital system. Step 1, you analyze the problem, develop the algorithm, and then write the program using your hardware description language. Now, this hardware description language, there are many languages. Most popular is Verilog or VHDL or System C. System C is becoming very popular these days because there is a reason behind it. It has been found that globally, people knowing C is available in large number. So those who are aware of C, it is much easier to teach them this hardware description language because System C has been designed in that way so that little effort will be required to migrate them from typical C to System C. So the cost will be less because less time will be involved to train them, because ultimately the success of a product in the global market depends on the cost of the product. And when you talk about the cost of the product, there are many components involved in that. And one of the major components in this high-tech area is the intellectual cost, means the human resource cost, which is the most expensive. So let's say 2 companies. One is Intel, another is Motorola. If Intel, by virtue of their R&D effort, can deliver a product in less time compared to the other, its competitor, then overall cost of the product will be less. And if overall cost of the product is less, then ultimately to the end user, you can sell the product at a lower cost. So this is the biggest competitions. And that means the total technological research is based on the customer satisfaction. This we have to understand. So here, the most important part when you design a system, a complex digital system, the first part, initial part, is developing the algorithm for the problem. That means understanding the problem and to translate to an algorithm. And then this algorithm will be translated to a programming language. So that is the reason System C is becoming very, very popular today. I suggest, in fact, you can also learn this because many US companies, they are looking for the people with the knowledge of System C. Anyway, so this is the structure of the FPGA. So FPGA consists of, just looking at the diagram we understand, it consists of these basic building blocks: CLBs, IOBs, and what else? CLBs, IOBs, and switches.
Yes,
Marks,
sir.
marks, sir.
Switches.
Okay, switches and marks. In fact, switches are made of marks, but in the upper level, we'll call them switches or the routing networks. Okay, through which they can be routed. But now, in fact, the advanced processors, they have something more than that. We'll come to it. Now, programmable logic devices, briefly, let me tell you, apart from FPGA, there are PLAs, PLDs, CPLDs. CPLD stands for complex programmable logic devices. They are also available, but after the emergence of FPGAs, all of them are becoming diluted. But PLA and PLA, PLDs, they are in fact required for smaller logic functions. They can perform smaller logic functions. They are in fact, because FPGA will be costlier. So if we need to design very small logic functions, which might be requiring few AND gate or gates, so there, why should you go for FPGA? Because FPGA is more expensive. So for those cases, you will be using PLAs or PLDs. Okay, but whenever you are going for very complex logic functions, then FPGA. So if we just summarize, we can say that programmable hardware offers a balance between flexibility and efficiency. That means it offers a balance between flexibility and speed, because potential concurrency in the algorithm can be exploited directly by mapping the algorithm onto architecture. So this is the basic difference. In fact, very often we get confused when we talk about processor. CPU is a processor, and this is also a processor, FPGA. But the basic difference is the typical CPUs are based on the von Neumann or Harvard architecture, whereas FPGAs are based on hardware executions, and concurrency is available such that concurrency in the algorithm is exploited directly by mapping the algorithm onto architecture. You can hear the references if you want to further study on that, mapping algorithm onto architecture. You can go through the papers of S.Y. Kung. Many papers are available. So FPGA architecture, major resources are configurable logic blocks, routing blocks, and IO blocks. So these are the three major resources as we have just discussed. Apart from that, there are some other sources like memory, multipliers, global clock buffers, and boundary scan logic. Let me tell you why these are required. Even using CLB, you can do multipliers, but dedicated multipliers, why we require? Can you tell what is, any of you? What are the major applications? What are the areas where we find major applications of FPGA? That is communications, means digital signal processing. So digital signal processing is the major area where FPGAs are used nowadays. And what is the basic function? What is the basic building block for digital signal processing? Multiplications and accumulations.
Make unit.
MAC
Yes, sir.
So multipliers take much more time compared to addition. So to do the efficient execution of digital signal processing, multipliers, direct multipliers are given in the FPGAs. That means many floating point multipliers are available as building blocks within the FPGA. Now, why memory? Because CLBs,
To reconfigure, yes. To reconfiguring the CLBs.
not only that, memories are required when you are using your FPGAs for image processing applications, then what? Because image processing is also signal processing, it's 2D signal processing. For image processing, you have to handle large number of data. For an example,
sir.
let's say you consider 1024 multiplied by 1080, one image frame. So to get the smooth function of the image, moving image, how many frames per second is required?
30.
30 or 25?
30
There are two
frames.
concepts.
25 or
There are,
30 frames.
okay, there are
Hmm.
two concepts, NTSC and PAL. In
Tell.
India, Europe, we use PAL. And in North America,
Yes,
we
sir.
use NTSC. So for NTSC, we need 30 frames per second. And for PAL, we need 25 frames per second. So that means per second, 30 frames, if we consider. So 30 into 1024 into 1080, that many number of pixels, isn't per second?
Yes, sir.
So
Yes, sir.
huge amount of, and per pixel, 24 bit, because each pixel consists of
RGB.
RGB, each of them gray level 8 bit. So 24 bit into this many number per second. So that means you need a very large amount of buffer to store the data. That is why this memory are required in the most advanced FPGAs. If you go to Xilinx, okay, today is no more Xilinx because Intel has purchased that company.
Sir, AMD.
Yeah, but in fact is under Intel,
Okay.
and this is Statics, one of the latest FPGA. So there you will find all these features. Now let's come to global clock buffers. Now why global clock buffers is required? The buffer is required because when you consider an FPGA, there are millions of gates, like millions of logic devices, smaller devices within the chip. So when the clock comes from outside, it has to, because there are a lot of CLBs, this clock has to reach to all the CLB for synchronizations. So in the process, what happens? From one CLB to another CLB, when it goes, there will be slight delay. So that's why clock buffers are there, such that there should not be any clock skew. All of them will be getting the same clock. And boundary scan logic, according to IEEE recommendations, each and every vendor's VLSI devices, they should provide the support for testing. And this is done by boundary scan logic. This is a must. Okay. So this must have to be complied with. So apart from these three building blocks, memory, multipliers, global clock buffers, and boundary scan logic are must. Okay. Within. So these are, so FPGAs consist of CLBs, IOs, these routing networks for switching, and these extra memory multipliers, global clock buffers, and boundary scan logic. Well, there are different types of FPGAs. I'm not going in details at this moment. I will go later on, later part. Now, what is the mechanisms of the CLB? how a logic functions can be implemented. Any idea? If you want to make a programmable logic functions, what is the way to implement that?
Using
Now,
memory.
yeah, memory can be viewed as a truth table. Because when we talk about logic function, how a logic function is described? A logic function is described by a truth table. From truth table, we do, using Karnaugh map and all, we minimize it and get the Boolean expression. But the basic fundamental thing is the truth table. So memory can be viewed as a truth table. Because memory is what? If we just look at, let's say, this is a memory at the right hand side. Let's say A, B, C, D. These are the address lines. And in each address, one data will be stored. How many addresses?
To the power 4.
2 to the
2 to the power 4, sir.
2 to the 4 means 16. Now each location will store something. So there will be 16 locations. Now let's say here the truth table A, B, C, D, when all of them are 0, then your output Z is 0, 0, 0, 0, 1 is 0. So we can make your truth table accordingly. That means in the memory, we can store like that. So in location 0, 0, 0, 0 will be storing 0. In location 0, 0, 0, 1 will be storing 0 and so on, whatever we want. Now, what is the advantage of doing in that way? The advantage is if this data we can store, let's say in EEPROM, then this particular logic function will be stored permanently. If we want to change it, we'll change the contents of EEPROM, because EEPROM is nothing but erasable programmable read-only memory. We can change it, we can delete it, and we can store it.
Yeah.
So high level of flexibility is achieved. So depending on my requirement, I can change the logic function. So that is the basic CLB. And here, let's say you analyze a very complex logic problem and divide the complex problem into some smaller problem, and each will be handled by one CLB. And then how these CLBs will be interconnected, that depends on that problem. So the problem you have described by a hardware description language. Let's say you want to design a very complex multiplier. You write the algorithm for that, and accordingly that will be divided onto these CLBs. CLBs will be doing these functions concurrently. They'll communicate. And how they'll communicate? Who is responsible for communications?
Switches. The routing network.
Routing network, sir.
This routing network. So that means depending on the particular function, this routing network, these routers will work differently. So we have two programmable devices. One is for routing. Okay. Another is the CLB. So by changing the content
Yes,
of
sir.
CLBs and by changing the direction of the routers, we can implement different kinds of functions. Of course, the compiler will do all these things. So you being an user of FPGA, that means what is the biggest advantage? First of all, your design time will be much simpler. It will take less time to come to the market, and risk factor is very less. Let's say you have designed a particular applications, say communication systems, and you find that your competitor has come up with a better system. Now, to sustain in the market, definitely you have to add some more features. Your R&D team will do all this research, but ultimately you have to implement it. Then what you can do, keeping the same hardware, you change the contents of the CLBs and change the routers, your FPGA will become a different hardware. So that is the biggest achievement. So just by simple changes in software, that gives a bigger change in the overall system. So that's why time to market is much faster, and risk factor is almost zero. Had it been a pure ASIC, after designing, you can't change it. Simply you have to throw it out. And that is the reason these are becoming very, very popular. So this is FPGA. Now, as I told you, that when you talk about mixed signal processing, it's not only the digital devices which matters. We have to think for analog devices also. Now, we'll be discussing the advantages and how these analog programmable devices can be designed. And after understanding it, again, we'll come back to FPGA for detailed hardware design of FPGA. So at this moment, we understood the concept of FPGA, the theme of FPGA, and what are the basic fundamental mechanism for FPGA. Now, to go out of this monotonous thing, let's come to analog. Then again, we'll come back to hardware and digital hardware. So reconfigurable analog circuits and architecture. Now, so far, we have been discussing about the programming features of FPGAs, the flexibility, and the reconfigurability. Reconfigurability because by changing the contents of the CLBs and also the switches, what we call mux, we can change the function of a particular systems. So that is called reconfiguration. So here firmware is basically the contents of CLBs and also the contents of the router, the mux. Because the mux, you know, the control logic of the mux, by changing it, the input can be routed to the output. For an example, let's say mux 2:1. That means there are two inputs and one output. And how many control lines? Only one bit controls. So by changing the control lines, either the upper input will be delivered at the output or lower input will be delivered at the output. That is a switch.
Yes, sir.
So here, analog circuits can also be reconfigured. Our traditional and these things were not valid some time back for analog devices. But today these things are no more true because analog devices can also be programmed. They can also be changed, just like your digital devices. They can be programmed. And so here, the reasons are same. If we say, why do we need flexible analog circuits? Faster design, development, and product ready time. Faster time to market. Economy. And due to rapid change of features in electronic systems, provision of changing the circuit by firmware has become an essential feature. So here today, it is a general law. We should have some means to change our electronic devices, be it hardware, be it analog, be it digital. And this changing the circuit is done by the firmware. So firmware is kind of bit level software. This is an essential feature. So this in turn requires flexibility or reconfigurability. and also faster prototyping. So before bringing a product, we must test it, what we call, in the language of engineers, we call it proof of concept. And this proof of concept is nothing but prototyping. And prototyping, that also takes time. So we have to make it faster. So when we think of reducing the cost of the product, we must have to find out what are the different parameters involved for developing a product. Each and every parameter's time has to be shortened. And then only the overall cost of the product will be reduced. Now, when you talk about analog devices, so let's first understand what are the basic components for any analog circuit. We all know that basic components are, what are the basic components for any analog device, for any analog systems?
Sir,
Sir, op-amp.
Resistors, capacitors, inductors, and operational
Yes, sir.
amplifier. And
Yes,
operational
sir.
amplifier.
Yes, sir.
Okay. And again, the operational amplifier, the basic things are transistors, and of course, resistance, capacitances.
Yes, sir. All the active and passive elements.
Yeah, all the active and passive elements. So here, this is the block diagram of the program, like basic adder multiplier. We all know that. This is an operational amplifier. There are two resistors, R1, R2. So this is a circuit of a scale changer or multiplier. But typically, this multiplier, in fact, here for analog circuits, we define two types of multipliers. One is constant coefficient multiplier, and another is multiplying two time domain functions. These two things are completely different, mind that. When you talk about constant coefficient multiplier, what is the example? Amplifier. Amplifier, for an example, your input is A, say 10 millivolts, and output is 20 millivolt. So what is the amplification factor? 2. Amplification factor is 2. And here we are multiplying by a constant 2. But when we are modulating two signals, let's say a carrier signal and a baseband signal, then what do you do? We multiply this carrier signal and the baseband signals. So this multiplication is not a constant coefficient multiplications. Here we are multiplying two time domain functions. So these are two different things, mind that. So here, in fact, the multiplier, what we are talking about, this is V out equal to minus R2 by R1 into V in. This is a constant coefficient multiplier. And this is an adder. The bottom circuit is the adder. So V out equal to minus V1 plus V2 plus V3, provided all the resistance are same. Because this R by R into V1 plus R by R into V2 plus R by R into V3, and overall it will be a minus sign because of 180 degree phase shift. So upper one is a constant coefficient multiplier and lower one is an adder with a 180 degree phase shift. So these all of we are familiar with. But if we want to make a programmable adder, so what we have to do? This R1, R2, they need to be flexible. That means this resistance will be flexible and they will be programmable. So how to make a resistor programmable? It's not possible that within the VLSI chip, just manually we will be changing the resistance value. That is not possible. So how it can be done? That is a challenge. And this is done by a switched capacitor concept. This was in fact a wonderful research which came, and now it is quite stable and quite developed. So programmable resistor, the concept is to make an equivalent resistor such that even a large value registers, which normally requires a huge amount of silicon area, will require much less area in a typical CMOS process. And the register is programmable. This can be achieved by switched capacitor. Now let's come to the concept of switched capacitor. In the left hand side, there is a diagram. Can you see the diagram clearly?
Yes, sir. Yes, sir.
Yeah.
Yes,
Now
sir.
here, we can see that there is a capacitor C, and there are 4 switches. Okay, in the horizontal, there are 2 switches we call phi 2, and vertically there are 2 switches phi 1. So when phi 2 will be on, phi 1 will be off, and vice versa. And these switches are controlled by clock. Okay, here you can see that phi 1 and phi 2, they're just inversion of that. Okay, so if we have a NOT gate in between phi 1 and phi 2, then we will find this thing. Now what we are going to do with this? You see, let's consider a simple resistors, and at two ends we have potential VA and VB. Simple Ohm's law, we know that current which will be passing through this resistor is given by VA minus VB by R. Let's say we will emulate the function of this by switched capacitor. How? Now in the right hand side, there's a capacitor and 4 switches, phi 2, phi 1. So let's say phi 1s are off and phi 2s are on. So what will happen? And there are two ends, VA and VB potentials are given. So what will happen?
The capacitor will get charged.
Capacitor will be get charged. Very nice. So how it will be charged? What is the formula? Q equal to C into V.
Yes.
C is the capacitance and V is nothing but VA minus VB. That is a potential difference between A and B point.
Yes, sir.
So we can say that current passing through this capacitor is given by Q by T. If T is the time period, okay, because current equal to charge by time, that is equal to, what is Q? Q equal to VA
Charge,
minus,
sir.
yeah, that is equal to VA minus VB by T. This is VA minus VB. Q equal to C into V. So this C into VA minus VB by T. So I equal to C by T into VA minus VB. We know that I equal to VA minus VB by R. So here we can say that R equal to T by C is equivalent to, isn't?
Yes, sir.
So R equal to T by C.
Yes, sir.
R is a function of what? The T. What is T? The time period of the clock. If the time period of the clock is lower, that means if the frequency is high, then what will happen? The resistance will be lower.
The resistance, yes, sir.
So that means by changing T, we can change the value of resistor.
Yes, sir.
So that means we can make a programmable resistor using this switched capacitor. So first, what we'll do? Let's phi 2 will be off, phi 1 will be on. Give this clock, the capacitor will be charged. Okay, once the capacitor is charged, the current will be flowing through that. Then what we'll do? After that, you just switch on this phi 2, the capacitor will be discharged. Again after that, you just switch on your phi 2, switch off phi 2, phi 1. So in that way, in every clock, it will charge and discharge, and it will be behaving like a resistance and given by this equation. So it's a programmable resistance. Now, anybody, any question? Because these are very fundamental questions, concepts. If you have, yes, please. Yes, yes. Yes, using mouse. Using mouse. No, no. This will be VLSI. Okay. Yeah, will be this option in fact. Now, yeah. So here the advantage is, yeah, uh, we'll come to the implementation also. So first, let's clear our concepts. What you said is correct. We are going in that way only. Now here, the interestingly, what are the MOS as a variable listed? Yeah, we'll use MOS as a variable listed. Now here, one thing is interesting. What are these switches? Here for concept, we have shown the switches. These switches are nothing but transistors. Okay, so there are two types of transistors, NMOS and PMOS. Because you must have noticed that what is the relations between phi 2 and phi 1? What are the relations between phi 2 and
Inverting,
phi
inverting, inverting.
inverting? So if we use here PMOS, here we'll be using NMOS, is it?
Yes, sir.
So that's what. So how many switches will be required? How many transistors will be required here altogether?
4 such.
So
right.
5 transistors, including capacitor, if we change it via P
Right,
or NMOS.
right. So altogether 5. Okay. But here, so that means using these capacitors, we are making a programmable resistors. That's why we call it switched capacitor. Now, typically, here I have taken an example. A capacitor is charged. Okay, let's set a clock frequency 100 kilowatts. So, using this formula, what is the resistance value? T by C equal to 1 by CF, R will be 2 mega ohms. So, it may be noted that a very large equivalent resistance of 2 mega ohms can be realized with a very low power dissipations. Because here power dissipation will be very low. So, it requires 2 to 4 transistors. Now here, why we are calling, how the transistors, number of transistors can be reduced? Because both of them, do you require two separate transistors here? This controlling? Because phi 2 are the same for both of them, isn't?
Yes, so phi 1,
Yes, sir.
This phi 2
phi-
and phi 1.
can we use only one MOSFET?
No, one you cannot use. You have to use two different transistors.
Yes.
Because NOT gate, you have to use the NOT operation, isn't?
So one for the 5 2s and another one for the 5 1s we can use.
So
But
means that
this phi
phi
1,
1 dimension will be same and the phi 2 dimension will be same for the transistors.
yeah. Okay, for the sake of simplicity, 4 transistors will make the job, isn't? Absolutely,
Yes,
there won't
sir.
be any problem. Then I'll come out. So up to this point, any questions? How the programmability
No.
is achieved? Okay. So what we are requiring for this, for making this? So this is a basic building block. Okay. Operational amplifiers, switches, capacitance that we require. If we just look at it,
Yes, sir.
well, why operational amplifier? That you understand, because these are the passive devices, isn't it? Because when you'll be cascading with another one, then signal level will be very low because you need operational amplifier to generate the. So these are the things you require. op-amp, PMOS, NMOS, and capacitors. And these capacitors will be done using transistors. Now, how this programmability will be achieved? The value of resistor depends on which parameters?
Sir,
Time period.
Time
time period.
and C. Let's say given a constant C, by changing T, we'll be changing the value of resistor. Now T is a function of what? What is T? Frequency.
We can change the
Yeah.
frequency.
Frequency of the clock?
Yes, sir.
Isn't frequency of the clock? How to change the frequency of the clock? How to change the
Also
frequency?
modulus?
No, simply by counter. Isn't?
Yes, sir. Yes, sir.
Simply by counter. So counter does what? So mod 4 binary counter divided by 4. Mod 2 binary counter divided by 2. So that is the basic frequency, and then you can keep on going, divided by 2, 4, 8, 16 or 5, whatever it is. So all that you have to design a counter. Okay. So by counter, and this is a programmable counter. How to design a programmable counter? What are the ways to design a counter? The students, what is your concept of designing a counter? I want to design a programmable counter. How to achieve it? Again, by lookup table. Why I'm telling you? Let's say I am to design mod 8 counter. Mod 8 counter, how many states? How many states are there in mod 8 counter? 8 states.
8 states, sir. After
So 3 bits will be required because log of 8 base 2 equal to 3.
yes, sir.
So 0,
Yes,
0,
sir.
0, 0, 0, 1, 0, 1, 0, and finally 1, 1, 1. So you consider a memory. Okay, lookup table. So let's say in 0, 0, 0 location you stored 0, 0, 1. In 0, 0, 1 location you stored 0, 1, 0. In that way, in 1, 1, 1 location you stored 0, 0, 0. Okay. So output of the memory 3 bits and use 3 flip-flops, 3 D flip-flops. And output of the D flip-flops will be connected to the input of the address lines. So first reset it. What should be there in the address bus?
0, 0, 0.
0, 0, 0. So what will be the output? 0, 0, 1, because in 0, 0, 0,
0, 0, 1.
you have stored 0, 0,
Yes,
1.
sir.
So that 0, 0, 1 will come to the input of the D flip-flop. That will be latched. So 0, 0, 1 will go to the input of the lookup table. So what will be the
Yes,
output?
sir.
0, 1, 0. So that's
0, 1, 0.
So that is a counter. And how programmability is achieved? You just change the state of the lookup table. Your counter would be changed. Isn't?
Yes, sir.
So just by changing the contents of the lookup table, you can make a programmable counter. So that is the concept of configurable counter using LUT and D flip-flops. That's what has been done. So depending on the need, you just change it and your resistance value will be changed. And this is your programmable analog resistors. So this is called configurable analog array. So we can call it CAB. What is CAB? Configurable analog block. For digital, we learned CLB, configurable logic block. And here we will call configurable analog block. So understand? Now, any questions? Fine. So let's say discrete time integrator. So our typical integrator circuits, the upper circuit, upper one, a resistors. In the feedback path, there is a resistors, and V output equal to minus 1 by Rn C integration of V in dt. That we are familiar with this. and time constant is Rin into C. Now, if we want to make a programmable integrator, what we have to do?
We have to, sir, replace the resistor with
We have
switch
to
capacitor.
replace the resistor by switch capacitor C, SC. And switch capacitor is what? Again, just look at this circuit. Already we have this. So this circuit, okay,
Yes.
this is called shunt circuit, parallel circuit. So here we'll put this circuit, and by changing this, we can change the time time constant of the integrator. Okay. So if we take the Laplace transforms, we know that what will be the transfer function? CS by
1 plus RCS.
Yeah. So that can be achieved here. So now this is, we have replaced these resistors by this circuit. This is called, so we can call it a discrete time integrator. Why we are calling it discrete time integrator?
Because our input clock impulse pulse we are giving here.
Yes, it is a discrete.
Yes.
Now we'll go, let's say we'll analyze it. So this is the circuit, isn't it?
Yes, sir.
This is the integrator circuit, and here our switch capacitor, and there are two switches. This phi 2. Have you seen that? Phi 1 and phi 2 are two switches, and transistors Q1 and Q2. These are two transistors input. Here is a cap, and C3 is the feedback capacitors. This. Now we'll analyze it, how it works. Now when phi 2 is off, then equivalent circuit is like that. Let's say when phi 1 is on and phi 2 is off, it looks like that. Capacitor will be, what will happen in this case?
Charge.
Capacitor will be charged. And output sides will be like that. V0, C2, and this is connected to the inverted terminal. This is the equivalent circuit. Let's say if
Yes.
this happens at n-1th instant, then at nth instant, this is the case. At nth instant, what we are
Yes,
doing?
sir.
This phi 1 switch is off. That means this is disconnected, and phi 2 is on. It's like that. Is it clear?
Yes, sir.
Yes,
Yes,
sir.
sir.
Achha. Why you are calling it
Yes,
discrete?
sir.
Because by means of these switches, sometimes this is on, sometimes this is off. So this is happening in the discrete instant. Okay. This is not continuous. This is discrete. So now we know the law of conservation of charge, because we know the law of conservation of energy. And charge can be converted to energy because half CV square. So you can say that the charge at n-1th instant will be same as nth instant, the total charge, isn't?
Yes, sir.
So what is the total charge? So Q at phi 1, Q phi 1 means total charge at phi 1. That will be equal to total charge in Q2. So what is this? At nth instant, Vn into C1 equal to C1 into V1 minus V0 N into C2, because this is in the opposite directions, first one. That will be equal to the second case, 0 into C1, because C1, this capacitor will be discharged, minus V1 N plus 1 into C2. Is it okay? Why you are calling it nth instant and N plus 1th instant? Because this is happening after this.
The next stage of n, sir.
Next stage of n. So now, if we take the Z transforms in mathematics or in signal processing, you must have studied
Yes,
that from n to, if we take Z transforms, then this will be V1Z into C1 minus V0Z into C2 equal to minus Z into V0Z into C2. That means the transfer function becomes, if we just simplify these things, this is C1 by C2, Z to the minus 1 by this. So that means delay unit. You are making a delay also using this concept. Z to the minus 1 is what? Is a delay?
Yes, sir.
Okay. So many functions, mathematical functions can be derived using these things. Okay. So low frequency behavior, this mathematics, you can go through it and you can find out. I can give you some problems, you can solve it. Instead of I solve it for you, you can do that. That means what I'm trying to tell you, that using this, configuring these capacitors and this, and by switching them in different configurations, different mathematical functions you can do. Mathematical function, why I'm calling it? That means some discrete functions for digital signal processing. Okay, that is discrete analog signal processing. Discrete analog signal processing that can be done by this, and these are programmable. Okay. By changing the timing of your switching, how fast you will be doing it? By changing this 5.1 and 5.2 clock frequency, you can make it programming. And these are the programming features of this switch capacitor. Is the integrator. So Hz equal to C1 by C2 into Z to the power minus 1. That is here. That is a tensor function. So that means here you can give a switch capacitor here and a switch capacitor here. That also can be done.
Yes, sir.
Yes, sir.
This is generalized switch capacitor circuit. That means you can make integrator. This switch capacitor SC2 can be pure capacitance and SC1 can be switch capacitor based resistor. So it will be what? It will be an integrator. You can make a differentiator just by reversing. You can make a scale changer if both SC1 and SC2 are made resistor. So all kinds of functions can be done by making SC1 and SC2 programmable. All right.
Yes, sir.
Yes, sir.
Yes.
So different configurations can be made. Now how this can be, I'm just coming straight away. So this applications to switch capacitor in discrete filter design. Now this filter for RF circuitry, these filter designs are becoming very, very important. And also for neural network, when I will go for the details of neural network, then you will see that why these filters are very important for designing these neural network circuits. Now, let's say we are extracting features. Okay. Extracting feature could be anything. You consider simple one-dimensional signal, speech signal. Now, when we are comparing the speech signal of one person with some other person, or from the voice sample, we are trying to determine whether this voice belongs to this person or not. You know, these days, a lot of hue and cry regarding the voice sample in the newspaper. We read, how they do it. Now, without using artificial intelligence, we do it by certain mechanisms. What are the mechanisms? We extract different features from the speech signal, from the voice signal. There are different features like what are the frequencies, what is the intonations, what is the pitch. So there are various. So one of the most important parameter is what are the different frequencies in a given audio signal. Now, to extract different features, different frequencies, you have to do the filtering. For a simple example, let's say a particular signal consists of 3 frequencies, F1, F3, F5, or F1, F2, F3. Now, to check whether F1 is there or not, we have to extract a filter, okay, low pass filter, where cutoff is F1, and then check whether F1 exists or not. Then a band pass filter in between F1 and F2, whether F2 is there or not. In that way, we find out. That means a filter design is a very important parameter. And if it is an analog domain, then we have to design the analog filter. So here, in fact, the switch capacitors are widely used in discrete filter design. For designing any discrete filter, what are the basic building blocks for designing filter? Adder or subtractor, multiplier, okay, and the delay. So these are the basic units we require. Now, using this switched capacitor, we can make adder, we can make multiplier, constant coefficient multiplier. Here, in fact, when we are talking about multiplier, in the filter circuits, we need the constant coefficient multipliers because yn equal to xn minus k into hk summation, and h is constant. And what is h? That is impulse responses. Okay, so that's why we need constant coefficient multiplications. And here we need a delay. Now already I have shown you how to make a delay using the switched capacitor. We know how to make a programmable ladder and how to make a multiplier. So using that easily we can design a filter circuits. The rest of the things are same like your digital filter. So if you know the digital signal processing, use the same concept here. Only thing is that instead of digital unit, use this analog units. Rest of the things are same. For an example, let's say an accumulator. What accumulator does? Continuous additions, isn't? If xn,
Yes, sir.
Yes, sir.
xn is the input signals, yn is the output signal, we can say that yn equal to summation of k equal to minus infinity to plus infinity xk.
Yes, sir.
So here, now this can be written recursively. So yn equal to yn minus 1 plus xn. What is the meaning of that? Whatever has been added up to n minus 1 instant plus the current input, isn't?
Yes, sir.
Because upper one, if you write like that, you have to go, you will keep on going up to infinity, which is not possible. But concept of, what is the concept of accumulations? Whatever has been added so far, with that the current input will be added. So that's recursively you can write yn equal to yn minus 1 plus xn. Now what is
Yes,
the
sir. The
relation?
previous input plus the current input.
The previous, what was the previous output plus the current input, isn't?
Yes, sir. Yes, sir. Sorry, sir. Yes, sir. Sorry, sir.
Yeah. So what is the relation between yn and yn minus 1? Yn minus 1 is nothing but one
Yn
delay
is the current output and Yn
and one
minus
delay and one delay. Yn minus 1 means one delay from
one.
yn. So yn is the output, get one delay, and this you add with this section. So this is recursively very simple circuit. Just one adder, one delay, and that's all. This is your discrete structures of the accumulator. So in that way, you can design all these things. So all digital signal processing functions can be designed in analog. Okay, I'm not going into all this, that you can do it by yourself. So basic blocks. So these are the basic fundamental blocks for FPAA. So far what we understood, that using switch capacitor, operational amplifier, and this kind of building blocks, if we have, we can make a basic fundamental block. And these blocks are called CAB, configurable analog block. And apart from that, for SC, to make SC, what do you require? What are the components for switch capacitor?
Switch capacitor, sir.
Capacitor and NMOS and PMOS.
Exactly. Capacitor and transistors. NMOS and PMOS. So switches. That's all. Very simple thing. Now, so these are switched capacitor, whatever you have talked about, this we are coming. I'll discuss this later on. First, understand the simpler things. AN231E04. This is a commercially available FPA from NRDG. NRDG manufacture dynamically reconfigurable analog devices. They first came in the market. And after that, many companies from Japan, they have also emerged with field programmable analog array. Now, from your concepts, so far, whatever you have learned, can you tell me how an analog devices will be configured and whether this FPA is an analog device or digital device or mixed signal device? Anybody?
Sir, I think FPA will.
Sir, it is a mixed signal device.
Why?
Sir, while we are writing the code to configure the internal blocks of FPA, so the code will be compiled via some digital device, sir. Because
okay, you are right. You are absolutely right. Because yes, FPA, what you have said is absolutely correct. Because ultimately, this FPGA needs to be programmed, isn't? What is here to
Yes,
be
sir.
programmed?
Yes, sir.
The
Yes,
programs
sir.
are basically the switch capacitors need to be programmed. Means your resistance value needs to be changed. How this resistance value will be changed? Depending on the T, the frequency of the clock.
Yes,
Now,
sir.
to change the frequency of the clock, what you have to do? The counter contents you have to change. Yes, sir.
Yes, sir.
And this can be done by this lookup table. The contents of the lookup table, if you change, the counter will be changed. It could be divided by 4, divided by 5, divided by 6, whatever you want.
Yes, sir. Frequency divider.
And router has to be changed. For an example, you want to design a complex analog circuit. So a complex analog circuit can be thought of combinations of or concatenations of many analog circuits. Output of one circuit will be connected to the input of another circuit, and output of that circuit will be going to the input of, in that way. So whenever you design any analog circuit, it's a network of circuits, isn't it?
Yes, sir.
Even
Yes, sir.
when you design, let's say, a 3-stage amplifier. 3-stage amplifier means what? If I assume that your total amplification factor is A1 into A2 into A3, that means 3 amplifier will be connected in cascade. Amplification factor of first one will be A1. Amplification factor of the second one will be A2 and A3, and they will be connected in cascade. But for connections, one essential and sufficient condition is output impedance should be low and input impedance should be high. Then only you can connect. 2 electronic devices can be connected in sequential, provided the output impedance is what? low and input impedance is
Sir,
very
low,
high.
sir, low.
That has to be there. And that is the reason we use the operational amplifier. So this is the fundamental law.
Yes, sir.
Behind that. Similarly, if you have a very complex analog circuits, these complex analog circuits, you can divide into some smaller part, and each can be handled separately, and they can be connected depending on the functioning of the problem. That's all. That means the router needs to be programmed. Say you have a chip. Within that chip, there are a lot of configurable analog block, lot of switches. But this connectivity of the switches are not constant. It will change depending on the function of the analog circuit. So this connectivity has to be configured depending on the problem, and that will be done by programming. So when you program the mixed signal processing systems, then some bit stream, okay, or the firmware, that has to be downloaded on the chip. And this bit stream consists of two parts. One for this programming these registers and all. Another is for programming the configurable switch. So combining these things together is called the total bit stream. And this bit stream is the digital. So some digital part must be there, and rest of the part is analog. That's why it is a configurable circuit, but it's a mixed signal circuit. No, up to that, any question?
Sir, I had one question. Can we make the gain of a operational amplifier using a feedback network, where instead of the register, can we use the switch capacitor in the feedback network and make the gain?
Yes, we can, because that is the whole idea, To make it programmable, you can make it programmable by using the switch capacitor.
Okay.
What we do in the operational amplifier, we use some resistors in the feedback path to control the gain of
Yes,
the
sir.
operational amplifier.
Yes, sir.
And this gain, that can be controlled by your switch capacitor also. Switch capacitor is nothing but a resistor.
Yes, sir. And you show us that the clock pulse, but this is discrete. But if the signal is in an analog continuous signal, so what happens in that case in the switch capacitor?
Normally what happens, I'm telling you, this here, even though it's a switched capacitor, if it is done very fast, it doesn't matter. Because let's say we are using an amplifier in the audio range. Okay. So there's a bandwidth. And
Yes,
if
sir.
it is done within that range, you won't be able to feel that. If it is within the perception of hearing, can you feel that? For example, when you talk about perception of vision, if the frames, 30 frames per second, placed in front of your eyes, you will feel that it is a moving motion.
Yes, sir.
Same will be that. But of course, it is discrete. It's not continuous.
Okay.
Only it depends on the applications. Okay. Because continuous or discrete, all depends on the applications.
Understood, sir. Thank you, sir.
Okay, so now what are the limitations? We should also know what are the limitations of this. Now, before that, first go through the commercial FPA Let's go to the features, then we'll understand what exactly these are. Before that, I'll show you a diagram. Yeah. So this is the field programmable analog array, FPA, basic building blocks for reconfigurable analog circuits. I've taken it from anadism. This is a courtesy of. Look, it's difficult for you to see, isn't it? So small, but I'm just telling you. Broadly, can you see the CABs?
Yes, sir.
Yes, sir.
These CABs are analogous to CLBs in FPGA.
Yes,
The
sir.
concept, yeah. If we just try to make an analogy with the FPGAs, so here the CLBs have been replaced by CABs. And here some input-output lines will be there. And here the input-output lines will be all analog input and analog output, because they are dealing with the analog signals only. Okay. And there will be a lot of switches within CABs. Now, to configure these CABs, we need some configuration bit stream. So there must be some RAM area where configuration bit streams will be downloaded. That means from the user's point of view, let's say you are a mixed signal designer. There's a language called VSDL amps or Verilog amps. I think I purchased one book in the library. If you go through the library, you will get that book, VSDL amps, and a CD comes with that book. And that CD will allow you to write your program and you can compile it. Okay, in that way, you can do some experiments using the mixed signal. So this is a lookup table. Can you see in the bottom lookup table?
Yes, sir.
Yes, sir.
This lookup table will store the bit streams for the CLBs. That's why these are connected with the CLBs. Okay. And also some data will be there for configuring the routers. So these are the basic blocks. So this is the structure of the FPA. Just look at this diagram carefully. Can you see the switches? Where are the switches? Here?
Sir, the interconnects.
The interconnects are the switches. And at the output, some operational amplifier has been given to just increase the signal level. Some serial lines are there. So these are the structure of the FPAs. Achha, one thing, Mihir is here.
Yes, sir.
Achha, Mihir, in fact,
Yes, sir.
you must have remembered that I placed an order for FPA purchasing.
Yes, sir. It's we have APA.
You have FPA. So have you
Yes,
started
sir.
doing the work using FPA?
No, sir.
Oh. So you can open that and do these things. Do some experiments on FPA.
Yes, yes, sir.
You can use the students. They can.
Sure, sir.
Okay. Anyway. So here, these are the routing architecture. Look here, some horizontal bars, some cross switches. Can you see here? These are the marks. So by controlling the marks, what you can do, let's say output of one CAB, needs to be connected to the other one. So this diversion can be done by controlling these switches. These are the crossover switches. These are horizontal global bus. So let's say the top CABs, the data needs to be transferred to the bottom one. That could be done by this through these switches. Uh, configurable analog block. Configurable analog block. So each CAB is basically the, again, once again I'm showing you the basic fundamental things within the CABs are like this. So these are so load the bit stream onto that. Here FPGA, FPAA will become that particular analog hardware. Now, as far as the project is concerned, in the project, you'll find this is a mixed signal. So analog and digital part, you can think of two different identity on two boards and can develop the whole thing.
Hello, sir.
Yeah.
Yes, sir.
Last 2-3 minutes I got disconnected. Can you repeat the what you said about the downloading the stream for the recording?
Oh, what I'm saying,
Yes.
that let's say you have a board, okay?
Yes,
You
sir.
have an FPA board. Typically, these boards are connected to the PC using your USB port, okay?
Yes, sir.
Or there are some boards where they can be connected through JTAG also. So first, what you have to do, you analyze your problem. Let's say you want to design a complex analog circuit. Now, some tools are available. Directly, you can put your operational amplifier, resistors, etc. in the pictorial form on the screen. You connect them, okay? Plug and play in that way. And from that, you can get the total formulations of the problem. And it will generate your programming language. Like you must be knowing that in many companies, because of rapid productivity, they don't write the codes in Verilog or VSDL. They give the state diagram, and directly from the state diagram, the Verilog code can be generated. Have you been familiar with this kind of things?
No, sir. I didn't know from directly we can
Yeah,
generate the code.
directly you can get the codes.
Sir, is it like we take those structures from the Dropbox and we attach those and we will get the Verilog code of it?
Look, you can draw the diagram, okay, state diagram of the whole thing, okay, and you can describe. There are some norms, of drawing all these things. Same state, then this, the way the state diagrams are drawn, exactly in the similar fashion, you can do it and you can get the code. Similarly, for analog circuit
Okay, sir.
also, you will have some icons of op amps, these, that, everything. You can draw that and you can get it, or you can write the codes in various languages, mixed signal language. Like one of them is Verilog amps.
Yes, sir.
After that, you check it, you simulate it, synthesize it, and then get the bitstream. A bitstream file will be generated, and then from this bitstream file, it will be downloaded onto the memory, configuration memory of the FPAA, and FPAA will become that particular analog circuitry. You can test it by giving some input signal at the input, some analog signals, and getting at the output. You can check in the oscilloscope and test it. I can give you one problem. You write the equations of a second order differential equations. Now, second order differential equation is nothing but LCR circuit, L di dt plus I into R plus 1 by C integration I dt equal to EIT. EIT is the excitation functions, that means the input voltage. So this will be the solutions of a differential equations. And using a very high speed oscilloscope, output probe, you can give it and check it. Okay. Or all that you can do, you generate a sine wave. A sine wave can easily be generated by giving the equation of a simple harmonic motion, which is nothing but
If possible, can you please take one session on FPA only so that we can understand FPA architecture and working principle more
we have
elaborately?
done that.
With an example, sir. That means how to download the bitstream in FPA, if possible, sir.
But possible, but I don't know what board has been purchased exactly. Okay. Because these will vary.
Yes, sir.
We have to see your manuals and all these things. Then a complete example can be taken. Otherwise, it will be theoretical.
Okay, sir.
So I can
Okay.
see, what are the things. One day we'll sit down in
Yes.
online. We'll see
Yes,
all
sir.
these things and waste.
Sure.
And you just collect that book from the library, that VHDL
Sure.
amps. There are in fact
VHDL.
lot of examples are given.
Sure, sir. Sure, sir.
Okay. Then we can discuss. Whole day we can discuss on that. That is, I don't know, I forgot the name of the author, but VHDL amps.
Yes, sir. I have that book. I got it from the library.
Okay. So we can discuss on that. We'll spend some time on that. First, let's finish this portion. Okay. And then we'll, because here in this lecture, my intention is to give you the concept of FPGA, FPA, and then neural network, the concept of that, then the architecture of neural network and this artificial intelligence. And these days you will find that AI processors, they are also coming, and they'll be connected to the PCs or notebook as an add-on processor. Like a couple of decades back, we must have seen that with most of the notebook processors or this math coprocessor was there. So now AI is coming in the similar fashion. Okay. So here, in fact, in this lecture, my intention is to talk about mixed signals in details, and then we'll come for a processor architecture, analog and digital, for this AI
Okay.
architecture. So for that, we'll give
Yes.
you the concept of AI, machine learning, and then we can discuss about FPA in
Sure.
details.
Okay.
Okay.
Thank you, sir. Okay.
So, so now, from today's lecture, if there is any questions from your sides, please. So next day we'll discuss in more details about FPGA, and then again we'll come back to FPAA. We'll finish that, and then we'll go into AI. Okay. So far, whatever we have discussed, if you have any queries or any question, please feel free to ask me. So here, in fact, if we have time, pulse-based design, that's a very recent research trend in CHP implementation. Some companies are also working. In fact, recently my current topic is we are working on designing a processor which will be, the processor will be designed in real time depending on the problem. It is a configurable processor. Based on the particular problem, intelligently using AI concepts in real time, it will configure itself.
Sir, what is the concept of the pulse-based design which is under?
We'll discuss this thing when we'll come. Is a basically pulse code modulations. These concepts will be there. It is yet to be, it's still in the research stage, not very well established. Okay. So first, let's understand which one is already established, that switched capacitor design. That we'll be focusing on, and I will just tell briefly what is the pulse-based design. These are, we'll discuss about pulse code modulations, and then we'll, yes. It can be done, but normally they don't do it. But I'm telling you how it could be done. Whenever two time domain functions are multiplied, they are normally done in a different way. Okay, let's first understand. Forget about switched capacitor. In a normal operational amplifier, using operational amplifier, how two time domain functions are multiplied. These are done by using logarithmic amplifier. Now, what is a logarithmic amplifier? We know that log A, yeah, that comes later on. First, let's understand the mathematics. Okay, our intention electronics is nothing but mapping mathematics onto circuits. We think in that way. So first, let's try to understand the maths. A and B will be multiplied by log A and log B will be added. So first, find out log A, find out log B. add them, then log A plus log B, that is equal to log of AB. Then you take anti-log, that is AB. That is the concept. Now we have to find out log A. So if input is A, how to get log A? What you said right now is correct. Use a diode in the feedback path. Why you are using diode in the feedback path? Because what is the diode characteristics? It offers the logarithmic characteristics, isn't? That's why you are using it. So output you will be getting ln A, ln B. Okay. So ln A plus ln B equal to ln AB. So use two logarithmic amplifier, then add those signals. Then you get log A plus log B, log of AB. Then use what? Inverse adder. After adder, anti-log. Anti-log means you just reverse it. The diode will be in the front, isn't? So that's all. Now here, what you are doing, while you are using a switched capacitor, what you have to do? Keep the diode as it is. Instead of resistor, you use the switched capacitor. Purpose is out. Is it? So anybody has any question? And here, and I have the materials here regarding signal processing. If you want to do discrete signal processing using analog circuits, here entire things are there. I have not repeated it since in the last semester I taught you DSP. That time I talked about all these circuits.
Yes, sir.
Okay. So if those who are interested, you can go through it, or if you want me, you can get back to me. I can tell you further. Okay.
Yes, sir.
Even you can think of designing a VLSI chip for mixed signal circuits. So can I stop for today?
Okay, sir. Sir,
Sir,
if you have
I have a
time, I
question.
wish to call you.
Okay.
Okay, sir. Thank
Okay.
you.
No problem.
Okay, okay.
You do one thing before
Sir,
calling. Just send me a WhatsApp message. Okay. Then we can find out the convenient time to talk. Okay.
Sir, right now after this meeting, I wish to talk to you.
Oh, yes. Mihir, you were talking about. I couldn't. Okay, fine.
Yes, sir. Yes.
I'll be here.
Okay, okay, sir.
Okay. When they leave, I'm here still.
sir, I have a question.
Yes.